Okay, hello everyone. I hope that you had a good spring break. So, as the school's policy, this course is also moved to the online. So, I will record the lecture, and then I will post it on the Blackboard or the designated places, and then you can watch this video to learn the course materials. And I will do my best for your successful learning. So please let me know if you have any questions, and I will announce my how to do the office hour in the next time. So let's start with a new concept. So until this time, we have learned that how to estimate the estimators, and how to evaluate the estimators, and using the various tools. And let's leave this is our current framework, which is the statistical inference. Now let's go back to the framework in Stat 5380, which is you have known the distribution and you know the parameter. And now here, so I'm gonna focus on what I'm gonna focus on today is about the behavior of random samples when we have large sample. So for finite sample, when we know the distribution of sample, we can derive useful results. However, we do not know the exact distribution in general. And when the sample size approaches to infinity, and then we can investigate the behavior of random samples and random variables, and derive useful results in the behavior of sequence of random variables. So now our question is to ask, what's the behavior of the random variables when sample size large, and can we derive the useful results when we have a large sample? So this lecture, and I think the following lectures will answer these questions. So let me introduce two definitions. So first definition is, so here now we have x1 through xn is not the random sample, but they are the sequences of random variables. So the xn, the sequence xn converges in probability to x, and we use the right arrow and the notation p to demonstrate this convergence in probability. So xn, right arrow, and then we write down p above the arrow, and then write down x to show that xn converges in probability if limit of probability that absolute distance of xn minus x is less than epsilon is 1 for all epsilon greater than 0. So this means that the absolute difference as sample size goes large, highly likely that distance is going to 0 that probability is going to 1. So next definition. So now the second definition is almost sure convergence. So xn converges almost surely to x, and then you use notation a dot s dot to demonstrate the almost sure convergence and as a notation. And then that is if this probability of xn minus x, the absolute distance between xn and x, that distance is converge, and that distance is the probability is with 1. So here, this almost sure convergence is that the xn is actually converges to the x with probability with 1. So we might allow that when the probability the xn is not equal to x, that the limit is not equal to x, is that the probability is 0. But you can then think as this is the xn almost approaching to the x. So these two definitions are different. So convergence in probability implies that the absolute difference itself is highly likely close to 0 when sample size is large. However, the almost sure convergence implies that the absolute difference itself is 0 with probability 1, which is much stronger than convergence in probability. So let's look at the example for this one. So we have sample space. So let's say we have sample space is the interval 0 to 1, and we have uniform probability distribution, and so we define the sequence x1 through xn as So we have a sequence that is the x1s is the s1s plus the indicator of 0 to between 0 to 1 to s, and x2s is the s plus now the interval for indicator is half of that in the x1s, so it's the 0 to 1 half of s, and x3s is s plus the rest of the interval in the x2s, which is the 1 over half and 1 to s, and x4s is the s plus 0 to, and then indicator 1/3 of s, and x5s is the s plus the indicator 1/3 and between 1/3 and 2/3 of s, and then the x6s is the s plus the indicator 2/3 and 1 to s. So you can think as the indicator 0 to 1 to s, and you have 1/2 in here. This is gonna be indicator 0 to 1/2 of s, and this rest is the indicator 1/2 to 1 to s. Now this is going to be indicator interval 0 to between 0 to 1/3 and s, and this is, let's say 1/3, indicator 1/3 to 2/3 of s, and this is going to be indicator 2/3 1 s. So you can see that each interval with respect to indicator is shrinking as n goes to large. So the length of interval is shrinking. So in this case, when we compute, this absolute difference, and then we can see that the so the probability of distance approaching 0 is going to 0. So here the interval with respect to indicator is shrinking, and when we compute, so here, okay, xs is equal to s in here. So when we compute this xn and minus x, this we can cancel out this s on here. So let's say if you think of the x1 minus x is going to be s plus the 0, 1 s minus s, which is indicator of 0 to 1 s, and x2 minus x is going to be s minus the 0 minus s, which is the indicator of 0 to 1/2 of s, and etc. And let's say, for example, if you calculate 6 minus x, this is going to be s plus indicator 2/3 to 1 minus s, which is the indicator of 2/3 1s. So we have sequence of indicators, and then n, when n goes to large, this a sequence of the indicator has the small. They are with respect to the very small intervals. So if you take up this probability here, that probability of distance distance approaching 0 is going to 0. So we have this probability that the xn, and the absolute difference between xn and x is greater or equal to epsilon is approaching to 0, which implies that which implies that the limit of the probability of between absolute difference x and between xn and x is less than epsilon is equal to 1. Okay, so here this means that this is means that limit n goes infinity, probability xn minus x, the probability of the distance, absolute distance between xn and x is less than or equal to epsilon. That limit approaching to that probability is going to 0. So which implies that this limit of the probability that the x and between the absolute distance between xn and x is less than equal to epsilon is equal to 1. But in this case, however, this here the extent does not converge almost surely to x. Here again, the xs is s, because no such s, there is no such s that xn converges to s, which is the xs. So x and s, if you compute x and s, for any s is gonna be equal to s or s plus 1. So the sequence of x and s is is fluctuating between takes only value between 0s or s plus 1. So it does not converge to xs. If it is the s, x and s is s, then distance is equal to 0, but the distance between x and s minus xs can be s plus 1 when the indicator is equal to 1. So the x and s takes the two values always, so it does not converge to, does not converge almost surely to xs, which is the s.